this lecture we are going to derive Viens formulas. In particular, we are going to look at Viens displacement law and Viens distribution, and both are done using thermodynamics. And as you must know, that thermodynamics does not really care about the details of interaction. It is a macroscopic theory. And let us look at these beautiful arguments by Vien, and he came very, very close to obtaining the true formula for the distribution of spectral density, and he was actually awarded Nobel Prize for this discovery. So, first thing is Viens displacement law. For this, he considered a spherical cavity which, let us say, is expanding or contracting by a very slow, very small velocity v. It could be either way, right, small velocity v. And so, he considered adiabatic expansion of a cavity which is spherical cavity, right. So, adiabatic expansion of a spherical cavity. Adiabatic means that delta Q, a heat exchange, was 0 at temperature T. What we have seen earlier is that if I have a cavity like this, right, it is applying a pressure. It is applying pressure P. When it is allowed to expand adiabatically, keeping it in equilibrium, right. So, I will be applying some force on it, and therefore, it does work. So, the cavity, or more appropriately radiation inside the cavity, does work as the cavity expands. So, as the cavity expands, it does work. If it does work, what should happen to its internal energy? This implies the internal energy U becomes smaller, because the work is done at the cost of this energy, because there is no heat being supplied, and this implies the temperature goes down. Volume is increasing, the temperature is going down. At the same time, if I were to compress it, if the radius was going down, the temperature would go up, because I will be pumping in energy. Something more happens. As the radiation inside bounces around the cavity, as it expands. So, you recall from your 12th grade physics, if a light or sound reflects from a moving wall, its wavelength changes, its frequency changes. So, any light at lambda, as it bounces, its lambda is going to increase, because frequency is going to go down. So, I can actually, by studying this adiabatic expansion, I can relate how much is the change in this lambda, and how is that lambda related to T, and that is what we did, and we are going to do it next. So, let us see now how these changes occur. When this cavity has radius r and a light ray is going such that from the center, if I draw a perpendicular to this, the angle where it hits is theta, and this light ray reflects again, and this is going to be pi by 2 minus theta, and so is this angle. Let me make it here again cleanly. So, here is the light ray which is going, this is the center, this angle is theta, and the light ray gets reflected like this, and the cavity is expanding in this direction with velocity v. Now, change in the wavelength is given by Doppler's formula, and v is much less than c. So, delta lambda over lambda is given as 2 v. The component of v is going to be taken in the direction of light, which is v sin theta. So, this is going to be 2 v sin theta divided by c. So, this is going to be delta lambda is equal to lambda times 2 v sin theta over c per reflection. So, during each reflection, this is the change in the wavelength, and I want to relate this to the temperature change. How do we calculate the temperature change? So, calculation of temperature change. This is done using first law. Of thermodynamics. Which says that delta Q is equal to delta U plus P delta V. Now, I am taking an adiabatic expansion. So, this is 0, and therefore, delta U is going to be equal to minus P delta V, which I can write as minus U by 3 times 4 pi r square delta r, where r is the radius of the cavity. Delta U is nothing but delta of U times V, which is going to be delta U V plus U delta V, which is delta U V plus U times 4 pi r square delta r. So, let us collect this all together on the left hand side, and we have delta U V is 4 pi by 3 r cubed plus U 4 pi r square delta r is equal to minus U by 3 4 pi r square delta r. All right. Now, I can write this 4 pi r square cancels from all through, 4 pi r square, 4 pi r square, 4 pi r square. So, you get delta U r by 3 is equal to minus 4 U by 3 delta r. So, this is the result we have got, which I will take to the next slide. So, we have got delta U r by 3 is equal to minus 4 delta r u by 3. This 3 cancels, and I get delta u over u equals minus 4 delta r by r. Now, I know that u is proportional to t raised to 4, which implies delta u is proportional to 4 t raised to 3 delta t. If I substitute that, I am going to get delta u over u is equal to 4 t cubed delta t over t raised to 4, which is 4 delta t over t. So, from this, combining all this, I get 4 delta t over t is equal to minus 4 delta r over r. This 4 cancels, and I get delta t over t is equal to minus delta r over r. dt over t is equal to minus dr over r implies immediately that t times r is equal to a constant. As the radius goes up, the temperature comes down. So, we have related temperature and radius, and we have also found delta lambda is equal to lambda 2 v sin theta over c per reflection, and we combine these two to relate lambda and t. Let us see how we do that. Delta lambda over lambda is 2 v sin theta over c per reflection. Now, for each reflection, the distance travelled by light is, if the radius is r, then time per reflection is 2 r sin theta, because this is r, this is theta. So, this is r sin theta, this is r sin theta. So, 2 r sin theta divided by c. Time per reflection is 2 r sin theta divided by c. So, the distance travelled by the cavity walls in this time is going to be equal to delta r, which is equal to 2 r sin theta over c times v, which is, I can write as 2 v sin theta over c times r. This implies 2 v sin theta over c can be written as delta r over r. Now, I will substitute this in this formula and get delta lambda over lambda is equal to delta r over r, or d lambda over lambda equals dr over r, and this immediately gives you that lambda over r is a constant. Let us check that. Lambda equals c times r, d lambda is equal to c dr, d lambda over lambda is equal to c dr over cr, which is dr over r. So, this checks. Lambda over r is a constant. So, what have we got? We have got t times r is a constant. Let us call this C1, and we have also got just now that lambda over r is a constant, which is some C2. We can combine the two and multiply both equations. This is equation 1 and this is equation 2. This tells me that t times lambda is equal to some constant. What does this mean? This means in this cavity, as it expands, the radiation remains at equilibrium. It goes from T1 to T2. If I look at a particular wavelength and keep following it, this lambda changes from lambda 1 to lambda 2. It will be such that T1 lambda 1 is equal to T2 lambda 2. This lambda has to correspond to certain feature of the radiation. So, the feature we choose, feature chosen to identify lambda is lambda max, and then we write lambda max times t is equal to constant, and this was confirmed by experiments carried out, and they found that lambda max times t is of the order of 2900 micrometer Kelvin. So, this was confirmed, and therefore, Viens analysis was correct. This analysis was also used for the first time to estimate the temperature of distant stars and things like those, because you could find in their spectrum where lambda max is and put that in this formula and find the temperature of that star. The second one is more important, and for this what Viens considered is that when from a high temperature T1, if I go to a lower temperature T2, a radiation which was contained between say lambda and lambda plus delta lambda, when to a radiation is shifted because of that displacement formula, some lambda prime and lambda prime plus delta lambda prime. The energy content in the first case T1 was u lambda delta lambda, and this became energy content in the second case, which is u lambda prime delta lambda prime, and I should be careful, this is at temperature T2. So, what we have is that u lambda at T1 delta lambda went to u lambda prime at T2 delta lambda prime. However, I know what the temperature dependence is. The energy content is proportional to T raised to 4. Mind you, I am not going to take a ratio of energy density, but energy content, and therefore, I am going to have u lambda T1 delta lambda over T1 raised to 4 is equal to u lambda prime T2 delta lambda prime over T2 raised to 4. That should be the ratio by Stefan-Boltzmann's law. What we are assuming is that the Stefan-Boltzmann law holds even for energy content in small intervals, all right. But you get your answer, and if it matches, you are on the right track. Okay. So, now you have therefore this relationship. Now, notice that lambda times T1 is equal to lambda prime times T2. Lambda plus delta lambda times T1 is equal to lambda prime plus delta lambda prime T2, and this immediately gives you, this together gives you delta lambda T1 is equal to delta lambda prime T2, and we will substitute this in this equation, and I am going to get u lambda T1, delta lambda is going to be proportional to 1 over T1 over T1 raised to 5 is going to be equal to u lambda prime T2 over T2 raised to 5. So, through the analysis of this curve and the way lambda shifts, we have found that u lambda T over T raised to 5 is same as u, let me call this primes, u lambda prime T prime over T prime raised to 5. Now, I also know that lambda T remains constant. So, this implies that u lambda T over that constant raised to 5 lambda raised to 5 is equal to u lambda prime T prime lambda prime raised to 5, and this is a constant, right. So, what we have got through this analysis, that u lambda T lambda raised to 5 is equal to u lambda prime T prime times lambda prime raised to 5 is a constant. What kind of constant is going to be? I know obviously that u lambda T depends both on lambda and temperature. So, this constant I am going to write as some function f of lambda T, because lambda T does not change as you go from one place to the other, and therefore, as you increase this cavity size, or if you change the temperature from one black body radiation to the other. So, this is going to be a function of lambda t in most general form. Otherwise, it would have been a constant throughout, but that would not give you u as a function of lambda and t both, and therefore, we put this, and this immediately tells you that u lambda t is of the form some function of lambda t divided by lambda raised to 5. This is Viens distribution law. This also tells you that since u lambda delta lambda we equated to u nu delta nu, and if you recall from my previous lecture, one of the previous lectures, we had obtained that u lambda was nu square over c u nu. So, u lambda is f lambda t over lambda raised to 5, which can be written as c raised to 5 nu raised to 5 is equal to nu square over c u nu t, and this implies u nu t is of the form some other function g nu over t. I have written lambda as c over lambda, which is t over nu, which can also write as nu over t times nu cubed. So, these are two forms that have been derived by Viens, that were derived by Viens. Important thing, and that I am going to write on the side, is what we have obtained is lambda t is a constant and u lambda t times lambda raised to 5 is a constant for each given lambda. So, if I am given the experimental curve for at a particular temperature for different lambdas, I can always find the curve at some other temperature, because as the temperature changes, I will find the corresponding lambda prime, which will be equal to lambda t over t prime, and then using this formula, which says that u lambda t lambda 5 is equal to u lambda prime t prime lambda prime raised to 5, I can find u lambda prime t prime. So, given experimental curve at one particular temperature, the experimental curve for spectral density, I can find the spectral density at any other temperature. That is the utility of Viens formula. We will analyze it further vis-a-vis experimental curves in the next few lectures.